what I showed here are the results of our test cases. So, of course, we implemented this package in ResMax, but we need to use a density modification and a model building program. For these test cases, we chose to use Parrot and Buccaneer, but we also have interfaces for ShellXE and Upwork as well. So what this slide shows is the fraction of the model that has been correctly built. On the x-axis is what current methods are crank 1, or the stepwise multivariate function used. So if the stepwise function was able to build things to a high degree, we see that the fraction is 1. So here are all models, for example, that the current methods of the stepwise multivariate approach built to a high degree. And here are, for example, cases where it couldn't build at all, not solved. What we have on the y-axis is the exact same thing, but this is using the combined algorithm that combines experimental phasing, density modification, and model refinement all into one. So if at 1, you see that it's built to a high degree. So again, here are about a third of the data sets where, and all data sets are shown with a blue circle. Here are data sets where both targets or both algorithms were able to build to a very high degree. So over 80% completion of the model, and these are about a third of all of our data sets. What we see here is another third where no method was able to solve. Basically, it was just a weak anomalous signal. So that's also about a third of data sets that we see here. So under 10% completion of the model. But we see also this third, the interesting bit, where over 80% is built with the combined algorithm, but under 60% is built with the current approach. So this showed us that there's a power in this method. So just to give you a summary, we see that with the new combined approach, we get an average increase from 60% to 74% with looking at all 150 data sets. But if we exclude data sets that were built to 85% by the current approach, or where the substructure was not found, we see about a third of the data sets, 45 data sets remain, where the average fraction of the model built increased from 28% to almost 80%. So this is a difference essentially between success and failure, which was very encouraging. So one test that we highlight is actually from collected and solved by someone at GRID at the moment, I think Keith Meyer. So he was looking at RNA polymerase 2, 12 subunits. This is a 3.88 angstrom data set, but it is actually anisotropic. And he could probably tell you more about the data set. I have that just summarizing it was the anomalous signal was from zinc. So the authors couldn't solve the structure with that data alone, but used a partial model, so the 10 subunit RNA polymerase, multi-crystal MAD, and manual model building. But we found just from the signal of zinc, so just using the zinc substructure, we could build to completion greater than 80% of the alphas with the STAT data alone, automatically using this new combined algorithm to an R3 of under 38%. So what we've shown here, maybe it's not so clear, but in colors is the model that was built by Crank 2 using Buccaneer, and you may be able to see in gray, but it's quite well superimposed with the alpha trait for the true structure, and you see that it's built to quite a high degree with the alpha position. Again, because it's only 3.88 angstrom data, we can't get the sequence that we get the alpha trait, and this is what it looks like. So what I wanted to talk about next is something that was also always a concern for Pavel and I when we were looking at this. We always thought, and some of you might have noticed as well, when you go in density modification, you will find that you always get maybe 0.8 for the figure of merit. So the figure of merit is very high, even if your final map is, lousy. And we thought, well, once we get over this assumption of independence that's being assumed in traditional density modification, maybe we can get actually realistic figure of merit. Unfortunately, this wasn't the case, and this bothered us. But one thing that's nice about using multivariate functions is you can introduce other parameters which you can accurately estimate and provide better error estimates to try to reduce bias. And this is something that Pavel has done and called he named data correction, which is applied to these errors that we use in maximum likelihood and refine in order to reduce bias of density modified data. And I show this graph here, and so what I have on the y-axis is the figure of merit that's reported by density modification. And again, in blue dots are all of the models that we see. On the x-axis is the actual cosine of the phase error. So the figure of merit is trying to estimate the cosine of the phase error, but we're calculating the exact cosine of the phase error on the x-axis. And basically what you see, even if the cosine of the phase error is very bad, so this is a 90-degree phase error, density modification will still report, a 0.6 or 0.8 figure of merit. And you see basically a straight line. It's always between 0.6 or 0.8, no matter how bad your phases are. This is without applying this bias reduction using the STAT function that we had implemented in ResMax. But if you actually use this bias reduction and get accurate estimates, you can see that now there's actually a relation between, it's almost like a diagonal line between the figure of merit and the cosine for the phase error. So we are actually able to get accurate estimates of the figure of merit, which is, of course, helpful in the subsequent subsequent model building process. If you get an accurate estimate of your phase error, you're able to get an accurate map. Okay, so now to the final part of my talk. I wanted to talk about using MRSAT and basically applying it in this combined algorithm. You may recall from the flowchart that I showed you, we can use information from a variety of sources and use it in this multivariate